In the last section, we talked about what happens if you have a finite geometric sequence. In this lesson, we're going to talk about an infinite geometric sequence. So notice this one's infinite because it keeps going. So with a finite geometric sequence, you've got a particular set of numbers and you're finding the sum of that particular set. But now we're going to talk about one where these values keep going and we want to look and see what happens. So here I've got a series and I can see that it's geometric because I'm multiplying by a half each time. So the rate on this one is 1/2. So let's think about the terms. The sum of the first term would just be 1/2. The sum of the first two terms would be what a half plus a fourth is, and 1/2 plus 1/4, I'm going to go ahead and just write these as decimals, is 0.75. So as we're writing these, let's go over here and put them on the graph. Let's see if I can't make this a little bigger. So I'm going to make this the term number, and this is the sum of the terms. So at the first term, we're at a half. When we add the first two terms together, we're at 0.75. I think I'll make these actually decimals. So instead of 1, I'm going to make this 0.1, 0.2, 0.3. And you'll see why in a moment. So let's see here. At one term, we're at a half, right here. When we add the two terms together, we're at 0.75, so that would be about right here. What happens when I add a half plus a fourth plus an eighth? Well, if you put that in your calculator, you get 0.88. Let's add a half plus a fourth plus an eighth plus a 16th. When you put that in your calculator, you get 0.9375. When you add that number plus 1/32, you get 0.96875. If you add that plus a 64th, you get a 0.9 something something something. So what happens here is at first we have a pretty large jump, but then it starts to balance out. Now what you're going to find is we keep adding we keep multiplying by a half, and so this number gets smaller and smaller and smaller that we're adding. So eventually it's like we're almost adding nothing to what we already have. So I would say that this one is actually not going to keep getting bigger. It's going to converge around 1 because it's getting closer and closer to 1, kind of like an asymptote does. This one is approaching 1. So there's a formula to find the sum of an infinite series. To find the sum, you take the first term and you divide it by 1 minus the rate. So let's see if that works on this one. So if I have the first term as 1/2 and I divide it by 1 minus 1/2, I have 1/2 divided by a half, which is 2/2, which is 1. Now, what would happen if, so we would say this one converges at 1, and we could see that on a graph, but what if it was a multiplier? So what if I was actually multiplying by 2 each time? And I wanted to add these together. This time, I would be adding a bigger and bigger number each time. So if this series was infinite and it had a multiplier that was bigger than 1, it would keep getting larger and larger and larger, and we really couldn't find the sum because the numbers never end. So whenever we're finding the sum of an infinite geometric series, we would say that if the rate, and we're going to say the absolute value of the rate in case this rate is a negative number, If it is smaller than 1, it's going to converge around a number. And we find that convergence by doing this formula. If that rate is bigger than or equal to 1, we would say that it has no sum. Another word for that, and what they'll use in Delta Math, is it diverges. So if I wanted to find the sum of this infinite series, I would first notice, by the way, you cannot put an infinity sign in your calculator, so you can't do the sum of an infinite on your calculator. So I want to find the sum of this infinite series. I know if it's infinite because it's going to infinity, and the rate is 0.1. Well, the absolute value of 0.1 is smaller than 1, so I know that this one is going to converge. And I can find the place where it converges by doing the first term, which is 2, because the first term will always be this number, divided by 1 minus 0.1. So 2 divided by 0.9, and 2 divided by 0.9 is 2.22. So this one converges around the number 2.22 because we would be adding a number so small that it's not going to change. Let's look at the next one. The first thing we need to do on this one is see if we can find the rate. 4 divided by 12, 1/3. 4/3 divided by 4, 1/3. So I can see the rate is 1/3 here. And since 1/3 is smaller than 1, I know that this is going to converge. If it was going the other way, it wouldn't, because it would be multiplying by 3 instead of 1/3. So the first term divided by 1 minus the rate. So 12 over 2/3. So 12 times 3 over 2 would be 18. So this one is going to converge around the number 18. So let's do one more just kind of basic problem here, and then we'll do a few word problems. So I have the first term is 5, and the sum is 27 over 5. So I want to work backwards then and see if I can find the R value. So I know that the sum converges when we have this. So this time the sum is 27 over 5, and the first term is 5, and I'm going to work backwards and find R. So 5 times 5 is 25, equals 27 times 1 minus R. So 25 equals 27 minus 27R. Negative 2 equals negative 27R. So divide by negative 27. So the rate on this one is 2 over 27. So you could see how it would converge because 2/27 is smaller than 1.